In this video, we will discuss why do chemical reactions occur. We will learn about entropy and the free energy change, as well as activation energy. Let's start with the spontaneity and free energy. Events that lead to lower energy states tend to occur spontaneously. For example, water falls downhill, releasing potential energy and reaching a lower energy, more stable position. Many exothermic reactions are spontaneous, for example, log burning in fireplace. The spontaneous reaction or spontaneous process means that it can proceed without the influence. So once started, proceeds on its own without any external influence. Spontaneous processes can be slow or fast. For example, rusting is spontaneous process, occurs spontaneously. However, this process is very, very slow. Or ice melting into water when the temperature is right. This is also a spontaneous process. A non-spontaneous process or reaction takes place only in the presence of a continuous external influence. The reverse of a spontaneous reaction is always non-spontaneous. To determine whether a process or reaction is spontaneous or non-spontaneous, we need to introduce a new quantity called entropy, or S. The entropy is the measure of the amount of molecular disorder in a system. The units of entropy are calories per mole Kelvin or joules per mole Kelvin. Endothermic processes have an increase in molecular disorder or randomness. What is endothermic process? Remember, we discussed the enthalpy of the reaction, delta H, or heat of the reaction, and we said that if the reaction requires heat is entering, this would correspond to the endothermic process. So for the endothermic processes, we have an increase in molecular disorder. For example, solid ice melts and water molecules are free to move around randomly. In this case, when we go from the solid state to the liquid state to the gas phase, the entropy increases. This is due to the movement of the particles of the molecules present in the solid or the liquid or in the gas. So in gases, molecules are moving randomly and they are free to move around. In liquids, molecules are able to move freely, but they are pulled closer to each other. In solids, molecules or particles or maybe ions are only able to wiggle just a little bit, so they are not able to move freely. Therefore, when we change a state from a solid to a liquid or to the gas, we increase the entropy or the molecular disorder in the system because of the movement of these molecules. Same thing happens when we increase the number of moles of molecules. What is mole? Mole is the counting unit, so increasing the number of moles will increase the number of molecules or atoms or ions. It means that the molecular disorder will increase. More molecules, higher molecular disorder. So we go from fewer moles to more moles, we increase the molecular disorder or entropy. And vice versa, if we decrease the number of moles or number of molecules, we decrease the entropy. The entropy change, delta S, is the increase in disorder or decrease in disorder as a chemical reaction or physical change occurs. If there is an increase in disorder, we show the positive sign for the delta S. If there is decrease in molecular disorder, then this is shown with the negative sign of the delta S. So delta S is going down. Here, delta S is going up. Increase, positive sign, decrease, negative sign. What can be predicted for the reaction below? Let's look at the coefficients of the reaction. On the left side, for the products, we have 2 moles of aluminum reacting with 3 moles of chlorine gas. On the product side, we have only 2 moles of aluminum chloride. So on the left, the total number of moles is 5. On the right, the total number of moles is 2. So we go from more moles to fewer moles, which means that the entropy decreases in this case. And a decrease in entropy is going to be shown with the negative sign. So A is the correct answer, entropy decreases, and delta S is negative. By decreasing the number of moles, we decrease the randomness of the system because fewer moles means fewer number of molecules and less movement associated with these molecules. We could also take a look at the states of matter. We started with solid aluminum and the gas, chlorine gas, and ended up having only a solid compound. So definitely this will decrease the movement of the molecules, right? In the gas phase, my chlorine molecules are able to move freely, versus in the solid compound, in this case ionic compound, ions are only able to wiggle just a little bit. So what factors determine the spontaneity of a chemical or physical change? To determine the spontaneity of a process, we need to take into account both the enthalpy change, delta H, and the entropy change, delta S. A release of heat favors spontaneity. Remember, what does the release of heat means in terms of the delta H? If the heat is released, we show the delta H with the negative sign. So I'm going to say favorable for spontaneity. The release of heat, or negative delta H, and increase in molecular disorder, or positive delta S, increase in disorder. Release of heat means exothermic process. So exothermicity favors spontaneity and increase in molecular disorder. More movement, essentially. When delta H and delta S are favorable, we say that a process or reaction is spontaneous. When both are unfavorable, a process is non-spontaneous. Sometimes a temperature also plays a role in spontaneity. To take both heat of reaction delta H and change in molecular disorder delta S into account when determining the spontaneity of a process, we use the free energy change delta G. The free energy change is a measure of the change in free energy as a chemical reaction or physical change occurs. In this slide, you can see my formula for the delta G, and it takes into account both the enthalpy change delta H as well as the entropy change delta S. But sometimes temperature can also play a role in the spontaneity. If the free energy is released, we say that the reaction or process is spontaneous, and the sign of the delta G is negative. If the free energy is absorbed, the process or reaction is non-spontaneous, and the sign of the delta G is going to be positive. The free energy change, or delta G, is sometimes called Gibbs free energy. The units of free energy are kilojoules per mole, usually, or kilocalories per mole. Notice the units of enthalpy. Enthalpy can be measured in kilojoules per mole or kilocalories per mole. The entropy is usually measured in kilocalories per mole Kelvin or joules per mole Kelvin or even kilojoules per mole Kelvin. But the temperature must be in kelvins, otherwise we won't be able to cancel the units of temperature. So let's take a look how heat of the reaction, the enthalpy change, and the entropy change influence the spontaneity. Let's start with the delta H. Positive sign of the delta H means that reaction is endothermic, it requires heat. Heat is entering. Negative sign of the delta H means that the reaction is exothermic and it releases the heat into surroundings. Now let's move on to the entropy change. Positive delta S means increase in molecular disorder, and this favors spontaneity, more movement, more spontaneous process. And negative delta S means decrease in molecular disorder, which is not favorable for spontaneity. So when both of these factors are favorable, the reaction is spontaneous. For example, if the exothermic reaction, the delta H, is negative, and if there is increase in molecular disorder, the positive sign of the delta S, the reaction is always spontaneous. So this means negative delta H, positive delta S. Always spontaneous reaction. If the reaction is endothermic, positive sign of the delta H, reaction requires heat. This is my positive sign. And there is a decrease in molecular disorder, negative sign of the delta S. Means that the reaction is always non-spontaneous. If only one factor is favorable, for example, either negative delta H or positive delta S, then temperature will play a role in spontaneity. So in case of the endothermic reaction, unfavorable positive delta H, but favorable delta S, increase in molecular disorder, the spontaneity depends on temperature, and this reaction will be spontaneous at higher temperature. If we have an exothermic reaction with favorable delta H and the heat is released in this reaction, but the molecular disorder is going down, so negative sign of the delta S. In this case, this reaction will depend on the temperature, and it will be spontaneous at lower temperatures. Let's look at the formula one more time. So for spontaneous reactions, we want our delta G to be negative. How can we get this negative delta G? How can we get this negative sign for the delta G? We can either use a large negative term for the delta H, right, which is an exothermic reaction. And then if the delta S has positive sign, we always get the negative sign for the delta G. If we are dealing with the endothermic process, for example, positive sign of the delta H, so if this is positive, then we need to make sure that our term, temperature multiplied by the delta S, is large enough to be able to obtain this negative sign for the delta G. So this needs to be large, and which means that temperature will play a role, and at higher temperatures, we still could obtain the negative sign for the delta G. This reaction could be spontaneous at higher temperatures, and so on. A spontaneous reaction or process that releases free energy is called the exergonic. So we can see the same similarity here. Exergonic energy is exiting, right? And the sign of the delta G is going to be negative. So we show this with the negative delta G. Negative delta G means the reaction is spontaneous. Spontaneous also means that once the reaction started, it will proceed without the external influence. Take a look at the picture on the right. I'm picturing the boulder here, and the spontaneous direction is downhill. It proceeds without any external influence. A non-spontaneous reaction absorbs free energy, so it requires an energy. This process, non-spontaneous process, is called endergonic, so energy is entering, and the sign of the delta G will be positive. So for the reactions with positive delta G, means that the reaction is non-spontaneous and it will require an input of energy. If you take a look at the picture on the right, a non-spontaneous direction is uphill, and it proceeds only if work is done, only if energy is entering the system or energy is going in. The reverse of a spontaneous reaction is always non-spontaneous, according to the law of conservation of energy. The energy is not created or destroyed, so the delta G value is going to be equal for the opposite process, for non-spontaneous process, but has the opposite sign. So the amount of energy that's needed for the reaction is the same, but the sign of the energy flow is the opposite. The direction of the energy flow is opposite. Some non-spontaneous processes become spontaneous with a change in temperature. Does entropy increase or decrease in the following processes? Complex carbohydrates are metabolized by the body, converted into simple sugars. Think about the number of molecules or the number of moles. We start with complex carbohydrates, and these are large complex molecules, so it means that we have less molecules at the beginning. And then these large molecules are metabolized by the body and converted into simple sugars, so into a lot of the simple molecules, more molecules, which essentially means that the degree of molecular disorder increases because of the movement of these molecules. More molecules means more movement and more disorder. So the degree of molecular disorder increases, the entropy increases. Second question. Steam condenses on a glass surface. Let's think about the changes in states. We start with the steam, which is the gas phase, and then the condensation going on means that the gas goes into the liquid phase. And we know that in the gas phase, molecules or particles are able to move freely, they are completely free, they don't actually interact with each other. In the liquid states, the molecules are a lot closer to each other, they are pulled closer to each other, and although they can move kind of freely, but they are not as free as in the gas phase. So in this case, the entropy is going down, entropy decreases. In the third question, we have a reaction of sulfur dioxide with oxygen gas, which produces 2 moles of sulfur trioxide. Let's take a look at the coefficients of this equation. So we started with 2 moles of sulfur dioxide and 1 mole of oxygen gas. Essentially, we have 3 moles of gas on the left of the reaction arrow. On the right, we have only 2 moles of sulfur trioxide gas, which means that we go from larger number of moles of the gas molecules, or more molecules essentially, to the fewer number of molecules, which decreases the entropy. So molecular disorder is going down, decreases. Delta S is going to be decreasing. When potassium is added to water contained in a beaker, the reaction shown above occurs, and the beaker feels hot to the touch. This reaction is. Here we need to determine whether the reaction is spontaneous or non-spontaneous, and what would be the sign of the delta G, of the free energy. So, the fact that beaker feels hot to the touch means that the heat is released. So the delta H sign is going to be negative for this reaction, which is favorable for the spontaneity. This is exothermic reaction. Let's take a look at the molecular disorder. On the left of the reaction arrow, we have a solid potassium reactant with 2 moles of liquid water. On the right, we have a solution of potassium hydroxide in the gas, which means that molecular disorder increases because we actually form some gas here, right? And the molecules in the gas can move freely. So I'm going to say delta S increases, and the sign of the delta S is going to be positive, which also favors spontaneity. So we can conclude that this reaction is going to be spontaneous, and we can show this with the negative delta G. So the C is the correct answer. Spontaneous reaction, and delta G is negative. Calcium carbonate, solid, decomposes to calcium oxide, solid compound, and carbon dioxide gas. We have values for the enthalpy change and the entropy change at 25 degrees Celsius. First question, we need to calculate delta G at 25 degrees Celsius in kilocalories per mole and kilojoules per mole. Does the reaction occur spontaneously? To answer this question, we just need to calculate the value for the delta G. If we get negative value of the delta G, it means that the reaction is spontaneous. Let's start with the equation for the free energy. We will also need to convert temperature from the degrees Celsius to kelvins. Temperature in kelvins will be equal to 273.15 plus 25 temperature in Celsius. This equals to 298 kelvins. Notice that the value of the enthalpy change is given in kilocalories per mole and kilojoules per mole, but the entropy change is given in calories per mole Kelvin or joules per mole Kelvin, which means that we need to convert the calories per mole Kelvin to the kilocalories or joules to the kilojoules. Otherwise, we will not be able to cancel units and use these units in the equation. Let's calculate free energy. 42.6 kilocalories per mole. This is the value of the heat of the reaction, delta H, minus temperature in kelvins, 298.15 kelvins, multiplied by delta S, or the entropy change. This is positive value, 38.0 calories per mole Kelvin. I also need to remember to change my units. I want to get rid of the calories. 1 kilocalorie is 1,000 calories. So if I'm converting to kilocalories, 1 kilocalorie over 1,000 calories. So this will cancel the calories. Also, kelvins cancel. So I have my answer for the entropy change multiplied by the temperature in kilocalories per mole. So now I can subtract this value from the delta H value. The value of delta G is positive 31.3 kilocalories per mole, which means that this reaction is not spontaneous. Now, using the same equation, calculate the delta G in kilojoules per mole. You should obtain a positive value as well. Our second question is, would you expect the reaction to be spontaneous at higher or lower temperatures? If you take a look at the formula here, the only way we can actually obtain a negative value of delta G is if we make this term temperature multiplied by the delta S a large negative value, a lot larger than the delta H. To be able to do that, we need to substantially increase the temperature. So this process would be spontaneous at higher temperatures. Let's now talk about chemical reactions. Free energy change, or delta G, tells us whether the reaction can occur, but it doesn't say anything about how fast a certain reaction is. For a chemical reaction to occur, reactant particles must collide, and they must have proper orientation of the molecules. If you take a look at the picture here, the effective collision is the one that has an oxygen directly facing a nitrogen here. So nitrogen is facing the oxygen. Because of this orientation, nitrogen-oxygen bond in new molecule can occur. So the new molecule is formed. If my molecules don't have a proper orientation and nitrogen is not facing the oxygen, in this case no bond can form. So particles or molecules need to have proper orientation. Some chemical bonds must break and some other form. Collision must take place with enough energy. It means that the molecules must have enough energy and speed for new bond to be able to form. If the molecules do not have enough energy and speed, the collision again will not be effective, so the bond will not be formed. The molecules don't have enough energy to collide effectively to make this bond. Many reactions with favorable delta G do not occur at room temperatures, and they require heat for the reaction to be able to occur. When we add the heat to the reaction, we increase the frequency and force of collisions. So what factor determines the reaction rate? How fast or how slow the reaction is? Let's take a look at the energy diagram. And here we have the free energy versus the reaction coordinate. You can see the energy level of the reactants and the energy level of the products. For this reaction to occur, my reactants need to be able to jump over a barrier. You can see there's a barrier here, and for this reaction to occur, my reactants must overcome this barrier. This barrier is called the activation energy. The activation energy determines the reaction rate, so it determines how fast or how slow the reaction is. And this is the amount of energy necessary for the reactants to surmount the energy barrier. If this energy barrier is too high, the reaction will be slow, even though it may be a spontaneous reaction. If the energy barrier is small, then the reaction is going to go faster because the lower barrier means that the reactants need to have less energy to be able to jump over the barrier. So the reaction rate is a measure of how rapidly a reaction occurs, and the reaction rate is determined by the activation energy. So the activation energy itself is the energy difference between the energy of the reactants and the maximum energy of the reaction. So this difference is the activation energy. And my reactants need to have enough energy to be able to surmount this energy barrier. Note that activation energy is not related to the Gibbs free energy. It's not related to the delta G. So the reaction can be spontaneous, but it can be extremely slow because these are two unrelated terms. The spontaneous reaction means that it proceeds without the external influence, and the sign of the delta G is going to be negative. You can see that my reactants here are higher in energy than the products. It means that when this reaction occurs, this extra energy will be released, and this is an exergonic reaction. The energy is released. This is a spontaneous process. But at the same time, the rate of the reaction itself will depend on the barrier of the reaction. So it will depend on the amount of activation energy needed. Let's now look at the energy diagram for endergonic reaction or non-spontaneous reaction. This reaction is non-spontaneous because it requires an input of energy. The delta G for this reaction is positive. Let's take a look at the energy of the reactants. My energy of the reactants is lower than the energy of the products. So my reactants are more stable than the product. And this means for this reaction to occur, I will need to input more energy. So this delta G is positive. The energy increases, right? Compared to the reactants, the energy of the products increases, and this requires an input of energy. That's why this reaction is endergonic or non-spontaneous. But again, the fact that this reaction is non-spontaneous is not related to the activation energy. The activation energy itself determines how fast or slow the reaction is. In this case, if we take a look at the amount of activation energy needed, we can say that this is pretty slow reaction because the activation energy barrier is pretty high. This is the barrier that my reactants will need to overcome for this reaction to occur. I'm going to say high activation energy, and this means that the reaction is slow. Once again, the activation energy is not related to the free energy. The free energy tells us whether reaction can occur or not, whether it requires an input of energy or it occurs by itself. But the activation energy tells us how slow or fast the reaction is based on the amount of activation energy needed or based on the activation energy barrier. Let's now summarize. Activation energy is the amount of energy necessary for reactants to surmount the energy barrier of the reaction. Activation energy determines the reaction rate, meaning how slow or how fast a certain reaction is. The higher the activation energy, the lower the number of productive collisions and the slower the reaction. So higher energy barrier means slow reaction. Lower energy barrier means fast reaction. The size of activation energy and the size of delta G are unrelated. The activation energy tells us how fast or slow the reaction is. The delta G tells us whether the reaction occurs, whether it's spontaneous or non-spontaneous reaction, but it doesn't tell us anything about the rate of the reaction. Shown is an energy diagram for a reaction with a small activation energy and products having less energy than reactants. And we need to specify whether this reaction is spontaneous or non-spontaneous, and whether it's exothermic or endothermic. Let's take a look at the diagram. The energy of the products, the energy is lower for the products compared to the reactants. It means that this is spontaneous reaction and the sign of the delta G is going to be negative. So this energy is going to be released. This is a spontaneous process. The reaction does not require any input of energy. So this reaction is definitely spontaneous. And if we think about the stability of the reactants and the product, in this case, products have less energy than reactants. Having less energy in chemistry actually means being more stable. So it means that the reaction produces the heat, and this reaction is going to be exothermic. So just by looking at the diagram, we can conclude that this is spontaneous reaction and it's also exothermic. We can also say that products having less energy, this means more stable than reactants. So the extra energy or the heat of the reaction will be released, and this corresponds to the exothermic process.